I'm presenting my final project for AERO 4842 Spacecraft Design II course at Carleton University. And my final project is a 3-axis seismometer designed to characterize the surface ice crust of Europa. So the seismometer consists of 3 mutually perpendicular geophones shown here. Each one consists of a hand-wound magnet wire coiled around a 3D printed cylinder held in a 3-axis stand also that was 3D printed. I'll just do a quick overview of the system first and then go into each part in detail. So then each jumper wire from each end of the geophones connects to some resistors to protect our electronics, and as well as the resistors in parallel form the system dynamics of the geophones in a way that we like, such that the output voltage of the system is proportional to the input ground velocity. In this case, desk velocity, but we will do some outdoor tests later on in the video. So then the signal travels through the resistors to 2 analog to digital converters. These are ADS1115 boards. There's 2 of them because each one can only handle up to 4 signals or 2 differential signals. Voltage is a differential signal. So the X and Y geophones are on one ADS1115 board, and then the Z geophone has a dedicated board. These boards transfer the analog seismic signals into a digital signal such that the computer can read them and record and analyze the data. And the computer in this case is a Raspberry Pi 3.0. I'm running it here. Each X, Y, and Z geophone has a neodymium magnet suspended in the center by 2 compression springs, and the same compression springs and the same magnet mass are used in each of the 3 geophones, and therefore any differences between these signals can be deemed to be differences in the polarization of the seismic wave incident on this instrument, and not differences due to the specific properties of each axis geophone. This 3-axis setup is critical for measuring the difference between P and S waves in Europa's crust. The XYZ seismic data is being plotted in real time, so if I strike the table here, we'll see the response. And I'll do it again. See another response. You'll also notice that the time to the microsecond is being plotted in addition to the 3 seismic responses. This is key to synchronize the time of the excitation to the time of the response as seen by the seismometer. And if we then place a seismometer outside, we can use this information to deduce the wave speed in the ground. You'll see that now.
Mm-hmm.
In this video, you can see that I'm exciting the seismometer placed on the ground from distances of 4, 8, and 12 meters. And then this data is plotted along with data from a second trial, and the distances between the excitation and response are compared to deduce the wave speed to be 64.1 meters per second.